Yep. So yeah, yeah. The UV. Yep. Yeah. Yep. Oh. Hmm? Um. If you want to use the Wi-Fi here, you want to use LRCCD. Yeah, so LRCCD is the SSID that you want to use, and then you use your student ID and your usual student password. That should sign you in. Alrighty. Okay. So we're gonna start today's lecture. Also, so today's lecture is just like all the other lectures. It is going to be, I will be putting a lot of Easter eggs. It's going to be Easter egg hunt. When it comes to the lab time. And for those of you who are listening to me, it's good. For those of you who are not listening to me right now, good luck with your Easter egg hunt. And I'm gonna get started here. All right. So. So are we ready to start the class? Okay, because it's going to be an Easter egg hunt today again. So I designed all the labs to be somewhat of an Easter egg hunt intentionally because I think that resembles what you kind of have to do at work too. You kind of have to figure out how to solve a problem by kind of connecting the pieces. All right, so what we'll do today is we are starting off with an instruction or two instructions that are kind of interesting in a way. Okay, so we're going to look at and xy as well as or xy. Okay, so we're going to start with these two instructions. So both of these are bitwise AND or bitwise operations. How many people have not encountered the bitwise AND versus the bitwise OR in your CISP 360 class? I would probably assume the entire class, okay? Yeah, because those are the bitwise operators and they don't talk about those. Um, so the way they work is really just a multi-bit gate, okay? So the next thing I can show you is how this is implemented in the processor, in the ALU. So I'm going to go to one of the window here and then just go ahead and start up Logic Sim with the processor. All right. Mhm. And we only need the ALU this time. There might be later on we might need something else, but I think the ALU is fine. So when you look at the ALU, there is a bitwise NOT operator here. This is a bitwise NOT. So let me click on it so that you can see how it is a multi-bit NOT gate. So this is a NOT gate, but it is not a single bit NOT gate. It is an 8-bit NOT gate, which means what it does is bitwise NOT. We have already talked about bitwise NOT. Okay, it's just when we talked about it, it has a different name. Okay, so can someone tell me what is the other name of bitwise NOT? One's complement. Very good. Okay, excellent. So it is exactly the same as one's complement, even though sometimes we call it a bitwise NOT. Okay, so that's bitwise NOT, and this is bitwise AND. This is also bitwise OR. I don't have a bitwise exclusive or, because, it's not really needed for the most part, but we have bitwise NOT, bitwise and bitwise OR. So if you want to know what they do, okay, you can just load up the ALU and then just experiment with it. Okay, I believe last time on Tuesday we talked about how to load just the ALU so you can experiment with subtraction. That was an Easter egg that I left for you so that you can answer the last question in the lab without having to manually figure out all the bits. Even though you should be able to figure out all the bits manually as well. All right. So if you want to find out how these work, once again, you can experiment with the ALU. So I'll just do one example, okay, so we can see how that works. So this is bitwise AND, which means if I want to use the bitwise AND operator, I need to figure out what select bit to use. So the way to figure that out is to click on one of these buttons or these wires, It is coming out of a particular output of the demultiplexer. You just have to hover your pointer out, so it's operation 4. So now we go to opcell, specify 100, which is 4. Click on ALU enable so that the ALU is actually enabled. So now we have established a path to bitwise AND. So now we can try to figure out what bitwise AND is going to do. So if I put a 1 here and put a 1 here, you can see the output is a 1 over here. If this is a 0 and this one is a 1, then the output is still a 0. If this one is a 1, this one is a 0, the output is also a 0. And then for the rest, 0 and 0 are all zeros. So do we have any questions about how bitwise AND operate? Okay, no questions. Okay, so bitwise OR operates about the same way. So now we switch back a little bit to talk about the instructions. So now we switch back to this instruction here. So now let me ask you this question. Does it make any sense if I allow that X and Y to be the same register when we perform bitwise AND, or bitwise OR for that matter? In other words, what is 1 and 1? 1. What is 0 and 0? 0. What about OR? What is 1 or 1? And 0 or 0 is 0. So it would not seem to make sense, right? To allow the same register to be specified twice because AND XY, which is computing the bitwise AND between XY and then store that back into X, if you specify the same register, it would appear that it does not do a single thing. Okay? But you will be correct from the register perspective. That is, it's not going to do a single thing. If you specify AND AA, AND BB, AND CC, and AND DD, it doesn't do a single thing to the register. However, it has a side effect. So this is one thing that we talked about on Tuesday as well, is every computation going through the ALU will affect the flags. The flags. Okay. So now we're going to take a look at how that is going to happen in this case. So I'll just keep this one. Okay. We are basically performing a 0 0 0 0 0 1 0 1 and bitwise AND with 0 0 0 0 0 0 0 1 1. So now the question is, how is it going to affect the flags? So can someone tell me how it is affecting the sign flag of the output? Yep, that's okay. The question is, what is the sign flag of the result, given that we are doing a bitwise AND between 0 0 0 0 0 0 1 0 1 versus 0 0 0 0 0 0 1 1. The most significant bit of the output is it is still a 0. Very good. So if I want the sign flag to be a 1, how should I change the input? This is bitwise AND. They both have to be ones. Very good. So let's check out whether that is the case, right? So if we make both the significant bits of in one and into both ones, you can see how the sign out is already a one. And that is going to be stored in the flags register. Okay. What about the Z flag? What do you think the Z flag will be when the output is 1 0 0 0 0 0 0 0 1? What do you think is the Z flag? The Z, it's going to be a 0 because the output is not a 0, and as a result, the 0 flag is going to be a 0 to say that it is false that it is a 0. Is that okay? So we take a look at the 0 and see, make sure that it is indeed a 0. So it is indeed a 0 because it is dark green. Okay. So the other flags are not quite as useful because it is not a subtraction nor an addition. So the carry flag really does not make any sense. Okay. At the same time, it is all because it's also not an addition or subtraction. So overflow does not make sense. Okay. And then if overflow does not make sense, the L flag also does not make sense. So those three flags, okay, what I just mentioned, the carry flag, the overflow flag, and also the L flag, they are not affected by bitwise operators. But the sign flag and also the Z flag are in fact affected by the logical, I mean the bitwise and bitwise or and also bitwise not operators. Are we good with this so far? Okay. So you're gonna need this information in order to do your lab. So I'm trying to be kind to tell you ahead of time instead of just kind of talk about something and have people not to take notes and then figure out that, oh, I do not know how to answer this question. Okay, so all right. Do we have any questions? No questions? All right, cool. All right. So the next thing is, okay, but this is the same for both, logical and logical OR. I mean, excuse me, bitwise AND versus bitwise OR. So that means if I make the input identical, okay, whether you specify bitwise AND versus bitwise OR will not make a difference. In other words, look at this output here. I have both inputs being the same, which is 10000101. This is exactly the same, and I'm specifying bitwise AND right now, and you can see how the output is exactly the same as the inputs. Yes? Okay, and that's kind of as expected. If I change the operation to use a bitwise OR, you will see that, oh, it doesn't make a difference because bitwise OR versus bitwise AND do not make a difference when both inputs are exactly the same. They will still give you exactly the same thing as the output. Is that okay? So that means, if I support one of the two, then I don't need the other one. Is that okay? In other words, if I support AND AA, then I won't need OR AA anymore because they achieve exactly the same result, and vice versa. Okay, if I support OR AA, then I won't need AND AA anymore. Let's talk about one more, which is compare AA. Okay, what do you think compare AA is going to do? So before we go there, let's go ahead and check out the instruction here and see what CMP, which is compare, what it is going to do. This is CMP. So all it is going to do is to perform the subtraction. We are subtracting y from x, but it doesn't store anything anywhere. Okay, that's all it does. It just carries out the subtraction so that the flags are affected. Yep. So you can look for anything, okay? Because once we perform a x minus y, which is operation 001 of the ALU, all 5 flags will be affected. The carry flag reflects signed, unsigned comparison result. The Z flag tells us whether the two operands are the same. Yeah, go ahead. Yes. So JCI will branch if the previous CMP sees exactly the same value of the two operands. Yes, that is correct. All right. But if I were to supply, the same register to both X and Y, do you think that would be a useful way to use compare? It would not be useful because if I compare a register with itself, the result is predictable. Okay, so let's see how predictable it is. Okay, let's count all the flags. So if I subtract a register from itself, okay, what is going to be the C flag? Will there be a um, borrow flag if I subtract a register from itself? No. So that means the C flag is going to be a 0. What about the Z flag? The Z flag is going to be a 1. What about the sign flag? The sign flag would be a 0. Okay. And what about the overflow flag, the O flag? It's going to be a 0. Okay. What about the L flag? Now that we know the sign flag is going to be a 0, the over flag is going to be a 0, 0 exclusive or with 0 is going to be a 0. So that means if you subtract a register from itself, the flags register is guaranteed to have 0, 0, 0, 0, 1. So what would be the purpose of doing that? There'll be no purpose of doing that, right? So that means if if I'm running out of these opcode here, 1110 000 both XXYY are zeros, 0101, 1010, and 1111. All of those opcodes can be repurposed for something else. Does that make sense? So can someone tell me from this opcode table, I have to make sure it is actually reflected. Yes, it is reflected. Can someone tell me which opcode or which instruction is repurposing all of those other patterns that I just mentioned? In other words, if we have both XX and YY being exactly the same, I don't need to compare a register with itself. What am I repurposing those opcodes for? The decrement, very good. Okay, so let me go to the decrement so that we can kind of focus on it. So when you look at the decrement opcode, which has exactly the same four uh, most significant bits, but the least significant bit pattern is different because with compare, you need to specify two registers, and that's why you have XX and YY because they are supposed to represent potentially two different registers. But when you look at decrement, I only want to decrement a register. So there's no need to specify two different registers. So I'm repurposing those particular bit patterns so that I can implement decrement X when I specify 1110 and then have both of these basically have a repetition of the bit pattern of XX. Yes. Um, JC and JZ, that would not be repurposed because they have a different most significant 4 bits. Because these are 1011 and this one is 1110. I'm not sure what you mean by that. Yes, yes. So that's a very good observation. Okay, the observation is 1011, 1011, but they are not repurposed from another pattern though. So I'm not hijacking. So in this case, decrement is hijacking the opcode from CMP. So let me highlight both of those rows so that we can kind of visually focus on those rows, right? Because if I did not hijack the opcodes, then I would have implemented, the actual opcode of subtracting a register from itself, which serves no purposes whatsoever, right? So the hijacking is to say, oh, since those particular opcodes are not really doing anything meaningful, I might as well repurpose the same opcode, but to do something different, to specify something different. And this is how decrement, something is hijacking opcodes from compare, because originally they would have implemented compare, but since those compare operations or the way the registers are specified is not useful. So I just repurpose those opcode to to mean something else. Yes. I wouldn't say this is overloading because what this means is the opcode 11100000, or otherwise known as E0. The microcode in the ROM is going to implement decrement A. It does not implement compare AA at all. Yes. Yep. Yes. Yes. So in the lab today, there will be some questions related to exactly that. So you have just answered one of the questions in the lab. Good job. So yeah, I was I was intentionally not mentioning, how or is, also hijacked so that you can actually do some of your own discovery. But since, somebody already points it out, I can now highlight those two rows. So or AA is actually quote unquote hijacked to mean increment A. So if you can actually write the instruction or AA, and it will generate the correct opcode, but the meaning of that opcode is not to perform a bitwise OR of A and A. It would actually be implementing increment A instead. Yeah, so that's a little bit tricky, right? So you have to kind of pay attention to this. What about AND AA? Do you think AND AA is hijacked? Yeah, AND AA is not hijacked. Okay, so AND AA will do exactly what A and AA is going to do, which is doing a bitwise AND of A versus A, and then store the result back into register A. Yes, because I need one of them. Because if I need to know whether a register is zero or not, I don't want to have to load something into another register and then do a compare. So instead, I can do an AND AA, and that can tell me whether the register is zero or not. Let me say that one more time. If you need to know whether a register has a value of 0, without AND AA, I would have to put 0 into a different register, perform a actual compare operation, and then look at the Z flag after the compare. But with AND AA, the Z flag is changed or is affected by the content of register A immediately. So I can save myself one, not having to use another register, and two, the actual opcode to do that. So I'm saving time and I'm also saving another register because trust me, in this class you'll be running out of registers really quickly. So you really don't want to have to utilize a register for something that you don't really have to do it. So so and AA is actually a really really useful combination, many times. Very useful today actually in the lab. Yep, go ahead. Oh, I thought you had a question. Okay, all right. So are we still doing okay so far? Okay, all right. Let's go ahead and talk about. By the way, how can I perform two's complement using the opcode here? So how what is two's complement? It's yes. So how? So let's just say whatever we need to perform a two's complement on whatever is already in register A, and we want to do it in place, which means I just need to store the result of the two's complement of register A back into register A. So out of all the instructions that are displayed here, can you figure out which two would be useful? Yeah, the not and the increment. Okay, very good. Okay. So I think I have sufficiently answered basically all the questions in today's lab. So I hope you guys have been taking notes. Okay. Exactly. What are we gonna do, right? Yes, we got a lot of stuff that we can do. We can talk about how to 3D print on a glass filled nylon and all the other stuff that kind of goes along with it. Or I can talk about compiling. Yeah, let's do that. So we are basically already done completely with von Neumann architecture and memory. This is still useful, so if you have not installed River Spider, on your laptop, or if you have not gotten it to work yet, okay, so we might want to spend some time to do that. Unfortunately, I don't have a Mac, so if you have a Mac and it's not working, I might need to borrow your Mac for a little bit, just to kind of figure out why it is not working. Yes, go ahead. It's the zip file. It's the zip file. It's in the announcement. Go to the announcement. There's a link. You kind of have to read the announcement. I cannot remember where I stashed it. Where did I stash it? Bottom. Okay, thank you. See, I write all this stuff here, and I cannot remember what I wrote. But that's exactly why I wrote it, so that I know I forget about it, and that's why I wrote it. So if you just kind of go here, follow this link, it gets you right to exactly what file to download. Yep. No, the for Macs it is the other one. I cannot remember where I stashed the instructions. Yeah, yeah, go to the share folder and download this file. The reason why there's no direct link to the zip file or the 7-zip file is because I'm still tweaking it. So if I put a link here to Google Drive, the moment I upload to another file to overwrite that file, the file ID on Google Drive is going to change. So that means all of this instruction is going to be outdated. So that's why I only tell you where to find it in Google Drive, and then once you get to the Google Drive folder, then you have to download the correct file in order to expand it and unzip it and get it to work. All right. So so we're going to talk about compiling now. Okay, so hopefully that is going to be it's going to be a fun topic. If people are taking this class, from let's say Folsom Lake, College, they use the x86 the x86 architecture. So to go from C code into x86 assembly code, you can just use the compiler. So that means that there's a really easy shortcut to get the whole thing done. But in this class, because I'm using an architecture that is not supported by GCC, so there's no such shortcut in this class. That part is just a kind of like side effect of using my own custom processor. It was not intentional. Um, does anyone know what I'm talking about? You can use GCC with a dash, I think uppercase S, so it would actually generate the assembly code corresponding to the C code, which defeats the whole purpose of a class like this, which is to teach you guys how to do it by hand. Huh? Um, the compiler does not have a backend of this processor. Now, for those people who go like, oh, that's okay, I can write the whole backend for GCC to compile to TTP, then I don't have a problem giving you an A. Huh? To disassemble, you don't. Yeah, but in case you want the actual source code, so that you don't have really suspicious labels, you can convert from bytecode back into Java. So no JavaScript, Java. There are those are called what kind of name do you think would be appropriate for those kinds of tools? You're given the assembly code and it will reverse back to the high level programming language. No, no, there's a different name for those. So without consulting ChatGPT, what do you think is the name of that kind of a tool? You you're given the machine code or assembly code, but it reverses back to the high level programming code. Decompiler. They're called decompilers because they reverse the whole process of compiling. They are extremely useful, in some legal applications, but in the United States, you have to be very careful because we have the DMCA, or the Digital Millennium Copyright Act, which means okay, so to be more exact, okay, the DMCA says if you do any work to reverse engineer any copy protection mechanism, whether you actually use it to make money or not, the act of looking into it and researching is illegal. See, the nice thing is this mic only records my voice, so Ilya's voice is not recorded. All right, so we'll go ahead and get started here. Okay, so we're going to start with some C control structures, and all of this should be something that you know already. So I'm going to test your knowledge. Okay, so in other words, if I give you this piece of code, if A is less than B, A plus plus, semicolon, B minus minus, semicolon, which part is what is the then statement? In other words, if A is in fact less than B, what is going to happen? A is incremented, and what if A is not less than B? If A is not less than B, B is still decremented. Okay, let's just pause here a little bit, okay? Because when you look at the indentation, especially for people who program in Python a lot, you look at this code, it would seem to imply that if A is not less than B, then nothing is going to happen, right? That's what the indentation is suggesting. But in reality, if A is not less than B, A plus plus is not going to happen, but B minus minus still happens. Okay? So does anyone want to tell me why that is the case? It has to do with the syntax of C++. Yep, go ahead. Not so much the next line, not the last line. Okay, it's not exactly that. Okay, it has to do with the syntax of C++. So that's why we don't talk about Python in this class. Well, try to write an operating system in Python then. No, you cannot. No. The answer is you simply cannot. The answer is you simply cannot because there's no way for Python to interface, or there's no easy way to interface assembly language code with Python. Then you might as well just program in C. You're trying to put a stick shift mechanism in an electric car. Why are you doing that? Why are you putting a little stick shift thing in an EV? Yes. Yes, you can write inline assembly code in C, but that is not what you need in order to write an operating system. Because there are places in an operating system where C simply cannot specify what needs to be done. Yes. All right. So getting getting back to where what we're talking about, the conditional statement. So this is the material that I prepare for my CISP 300 class. This is not even 360. This is 300. Okay. Yes, some people may end up feeling a little bit bad about this, but that's okay. That's kind of my contribution here. So let me look at the CNF right there. Okay, very good. So this is the BNF, which stands for back nor form, which is a way to express syntax, otherwise known as the meta syntax of a programming language. So everything that is boldface is called a terminal, which means you just okay, since you're taking a picture, I'm moving out of that picture. So boldface means it's a terminal. Italic means it is a token, which means it can expand to something else. So when you look at the syntax of a conditional statement, we all know about this part. If spell it out, okay, if you need to put the condition inside parentheses. Okay, not a problem. And then we have a then statement. So now the question is, what is a then statement? A then statement is a single statement. If you say A plus plus with a semicolon, it is a single statement. Okay, so C syntax specifies, any assignment operation, if you end it with a semicolon, it is a statement. And that's why, in the code that we were talking about, which is, where did I put it? Oh, this is a different class. I have to switch back to our class. Okay, there we go. So that's why the A++ semicolon is already meeting the requirement of the then statement. Now, when the compiler gets to B minus minus, it will say, oh, optionally you might have an else branch. But an else branch always has to start with the terminal or the word else, ELSE. Well, B is not ELSE, so the compiler automatically knows that this conditional statement does not have an else branch. If it does not have an else branch, then the compiler would automatically conclude that we are done with the conditional statement. So B minus minus does not belong to the conditional statement whatsoever. Is that okay? So I think this is really important because that means if you have only one thing to specify in the then statement of a then portion of a conditional statement, I still encourage people to use the braces just in case you need to add something else later on. Then you don't have to worry about, oh, I need to add braces now. Just put the braces in all the time. Okay, so that would be my recommendation. So this is important, okay, because now we can move on to the actual thing that we need to talk about. So I hope everybody still understand what this statement means. Okay. Now obviously C is just a placeholder for a condition. Block one is a placeholder for a block of code that you want to specify for the then statement, and then block two is a block of statements for the else part of the conditional statement. So block one, block two, and C, they're all placeholders. Um, so I want to translate this code into something that do not use braces. In other words, I'm getting rid of the structure of structured programming because that is what you need in order to translate structured code into assembly code. So now the question is, do we understand the second block of code? Do we understand this block of code over here? Can we establish that this code down there would do exactly the same thing as the code up there? Okay, so say again. Yes, so L1 is right here, which is at the beginning of what used to be the else block of code. So if C is false, I go to L1 and L1 would perform whatever the else block is supposed to do. What if C is true? If C is true, then not C is going to be false. If not C is false, then the then statement of this conditional statement is not going to happen, which means we just fall through to block one, which is corresponding to the then branch of the original code. But this one is important too, because you need to make sure that you do not pass through to block two, and that's why you need to go to L2 after block one, so that after the then branch executes, we don't fall through to the else branch. Yes, but I don't want to specify block two because the whole point is to get rid of the concept of structured programming, which means I don't want to have to use braces. Do you okay? So the whole point is I don't want to use braces because guess what? In assembly language programming, there are no braces. There's no way to say, oh, this entire block of code has to be treated as one thing. There's no way to do that. Yes. Yep. It might do some kind of nifty trick to make it a little bit more efficient, but the general idea is yes, when you write code like this, the compiler will automatically generate the code equivalent to something like this. Yep. Why? I don't understand why we're going back to Python. But that's a syntactic thing. Okay, so when I said you're getting rid of the braces, it is a syntactic thing. Basically, we do not need structured programming. Python is structured. Everything at the same indentation level is considered to be one thing. That is structure. Okay, if you guys want to see this as unstructured code, let me present it. Yeah, because I see that as a challenge. It's like, Jack, I challenge you to make this not structured. Okay, fine. The for loop. Oh, that's pretty structured. I mean, that's like that thing has what? It's nested, and everything that is nested is structured. Move to other monitor. There we go. Okay, there we go. Okay. So one thing that I really emphasize in CISP 300 again is line feed has no meaning whatsoever in C++. Okay, every line feed, which means at the end of a line that opens a new line, you might as well use a space. Okay, because to the compiler, there's no difference between a line feed versus a single space. So that means the second piece of code without any braces can now be expressed as if not C, go to L1 semicolon block 1, go to L2 semicolon L1 colon block 2 and semicolon and then L2 colon. That is not structured. Hmm? Yes. You can put the whole thing on a single line. The C compiler does not care. Sorry. Sorry. Say again. Well, I just did. So I hear a challenge that I have to change the rest of this entire module so that there's no line feed in the C code. I can do that. What the class would end up doing is they will copy and paste that code into a pretty printer, so that everything looks right again. All right. So that's a conditional statement. But the point is, do we understand how the original code, which is structured, looks nice, is actually functionally the same as the second piece of code? Because this is how we gradually convert high level programming language code into assembly code, which is also known as the process of compiling. So are we good with this? Okay, excellent. So if there's no else, you can kind of shortcut a little bit. Okay, so if there's no else, you can simplify the block to look just like that. You're looking for an excuse to skip over the then branch, so you're just looking for a reason to go to label L1 and therefore skipping block one. So yes, you can optimize it a little bit if there are no else branches. Yes. Doesn't Well, L1 is just representing a continuation point because in this example I'm not illustrating what code might be after the original conditional statement. So L1 is simply saying, oh, okay, there's nothing to do with this conditional statement. Whatever needs to be done next is over at L1, but I don't know what that is. Huh? Well, then it's going to do the same thing as whatever the original code is going to do, which is there's nothing else. Yep. All right, so that's conditional statement, and then we have pre-checking loop, otherwise known as a while loop. So once again, we have the original C code, looking very nice. While C, open curly, open brace, block one, which is the block of code that we are supposed to perform, repetitively potentially, and then close brace. So that code translates to something a little bit more awkward this time because L1 is needed in order for me to have a label to go back to so that it does make a loop. And then I'm looking for an excuse to exit the loop. So I say if not C, go to L2, and L2 is a label that is after the loop. Block 1 is still the body of the loop, And then go to L1 is needed here because after you perform the block of operation, without the construct of a while loop, you have to specify, oh, we have to go back to wherever label L1 is in order to check the condition again. Yes. No, this is a while loop. Do until. No, this is a while loop. It is a pre-checking loop. Do until implies it is a post-checking loop. This is not a post-checking loop. You're still checking the condition first. Yep. Oh, quick. You're good. All right. So now we are we good with pre-checking loop, otherwise usually known as just a while loop. All right. So we are not going to talk about a for loop in C++ because in C++ a for loop is really just a fancy version of a while loop that allows you to specify initialization, the condition, and post operation, all within the parentheses. So that means any for loop can be translated into a while loop plus some initialization and some post operations in the body. So that's why I'm not going to talk about a for loop in this case. Now, for loops in other programming languages can be very different. So, the equivalency between a for loop and a pre-checking loop is only valid in certain languages, but in C++, it certainly is applicable. Yes. Oh, you mean above with the conditional statements? Okay. L2 is a label that is defined here. It marks the end of the entire conditional statement. So whatever is here, right after the close brace, after the else branch, is where L2 is supposed to mark. Yep. Yes. Yes. So without an explicit unconditional branch of L2 in this case, it will just kind of fall through to block 2, which is not the behavior of a conditional statement. So that unconditional branch to L2 is essential when you are specifying a conditional statement. Yeah, that is block 1. So block 1 should execute if and only if C is true. But this preserves the meaning, even though it looks a little different. Yep. Yep. Yes. So we are gradually breaking down, code that is written in a high-level programming language to the point where we can, implement, everything using the TTP ASM instructions. Yep. So because goto is really just JMPI, and the label definition is exactly the same as you would do it in assembly code as well. Yep. So we are gradually kind of breaking down, a C program in this case into assembly code. The nice part about this approach is if you do this gradually, in other words, if this is the original code given to you and you perform the translation into this can still be tested as a C program because it is still a C program. It's just an uglier looking C program. Okay. So that means if you do this process gradually, you don't have to switch to assembly code debugging until very late. So all these steps can still be tested using just a regular C, GCC, or code blocks or whatever environment you want to program in C. So that's a huge advantage, because otherwise you're going to have to, oh, okay, now we're converting this code directly into assembly code. So how do you test the assembly code? It's harder, okay? You can, but it's harder. So this can delay that process, having to actually debug assembly code until much later. So we good so far? All right. So getting back to while loops, same thing. Okay, if you're given this code originally, and you convert it into this code here, this is still C code. It will still compile with a C program with a C compiler. So that means if you want to check to see if you have accidentally put in a bug in the translation process, you can still use GCC along with GDB, use CodeBlocks, use VS Code, whatever tool you want to use to confirm that in the translation process, you have not introduced a bug into the program. So I would highly encourage people to do that, at least initially, until you get a really good sense of how to do the translation. Then you can do it in your head and not have to go through the intermediate process. So the last one, the last control structure is called a post-checking loop, which we know as a do-while loop. So it translates to something that's a lot easier in this case, because the purpose of L1 is simply to have a landing place, okay, to go back to the beginning of the loop. Block one is block one because this is a post-checking loop, so we have to perform block one anyway. So might as well just do it. And then we just have a conditional branch to go back to L1 because if C is still true after block one, then we have to go back and repeat block one, which is preserving the meaning of the original do while loop. So that's all. I mean, these are all the control structures that I am concerned about in this class. So your homework assignment, okay, is mostly me giving you the C code, and your job is to translate that into assembly code. All right. So now the question is, what about Boolean operators? So if you have a Boolean operator, given that C can be a very complex expression, because remember, when I use the letter C, it can be a placeholder for a very complex Boolean expression. So now the question is, so how do we translate that into something simpler without the negation? So in this case, it's usually pretty easy. If not C equal to L1 is the same thing as this block of code. It just looks uglier because if C is true, then we go to the continuation point of L2. If not, if C is false, then it's not going to go to L2 because go to L2 is the then statement of the if. So if C is false, we are not going to go to L2, which then means execution falls through to go to L1, accomplishing exactly the same thing as the original statement. In other words, I'm sacrificing um, control structure complexity to reduce the complexity of the expression. Yes, we don't care. We just say that if the original code says, if C is false, go to label L1, wherever the L1 turns out to be, we translate that into the second piece of code, which is highlighted. So the use of L1, L2 is completely localized, which means L1, L2 by themselves do not have any specific meaning in each snippet of code. All right, cool. Yes. Hmm? Assembly code? Not yet. So the only thing you can translate into assembly code right away is go to L1 because that's just JMPI to label L1. And then the definition of L2 is also, directly translatable into assembly code. But there's no such thing as an if in assembly code. The only conditional branches you have are, what did we talk about on Tuesday? JCI, JZI, JSI, JOI, and JLI. Those are the only 5 ways to perform conditional branches. So everything has to boil down to those 5. If you need to specify, oh, sometimes we need to go here and other times we need to go over there, they all have to boil down to a combination of these 5 along with potentially unconditional branches. Okay, all right. So What about or? In other words, what if the original condition in the conditional statement involves C or D? Now remember, C, D are both placeholders. Each one can be a very complex expression. So that means we are only reducing one level of complexity with each step. Okay. So in this case, if the original expression of the conditional goto is C or D, then we break it down to if C by itself, go to label L1, and then if D, go to label L1. Is that okay? Are you convinced that the new code would do exactly the same thing as the original code? Okay, but this example is actually interesting because it also explains how short-circuited logic works or short-circuited Boolean expression evaluation works. Have you guys been exposed to that concept, otherwise known as lazy evaluation? Short-circuited Boolean expression evaluation, which means in the case of an OR, if the left-hand side is true, we don't bother to evaluate the right-hand side. Because if you have an or and one side, the left-hand side, is true already, then the whole expression is guaranteed to be true, which means there's no need to evaluate the right-hand side. Most people think of this only as a quote unquote optimization thing, but it is actually very important to understand this. Because if D as an expression is an invocation of a function, okay, then the function call itself may have side effects. And as a result, whether you get to D or not can can have a lot of consequences. So that means understanding that um, C++ and most other programming languages implement short-circuited evaluation is actually really important. It is not just a matter of, oh, this makes it go faster, but it actually has a lot more implication in addition to being faster. Yes. hmm So goto does not have a mechanism to return. Yeah, so goto is really just a JMPI. Once you get to the destination, you cannot keep track of where you came from, and there's no way to go back. So when we need to talk about function calls, which is kind of like the next topic, then we'll talk about the mechanism of how do we keep track of, oh, this is a call, but how does the called function know where to return to? So we'll talk about that when we talk about calling and returning. So we talk about the control structure first, and then we'll talk about function calling, which involves as a short discussion of the stack concept. All right, so the next one is and. Okay, what if the original conditional goto is, the condition of the conditional goto involves your C and D. So we translate that into if C is false, go to L2. We got nothing to do because if the left-hand side of the and is false, there's no need to evaluate the right-hand side. This is also short-circuited evaluation. So short-circuited evaluation applies to or as well as and. And this is also why in the multiplication, the order of evaluation of the left-hand side versus the right-hand side is up to the compiler to decide. The compiler can say, I'm going to evaluate the right-hand side first, and then I'll evaluate the left-hand side, and then we just perform the multiplication and get the product. Same thing for addition, subtraction, and so on. But when it comes to logical operators like and versus or, it is always left to right. It is part of the language specification that with logical and logical or, the order of evaluation is always left to right. And that has to do with how code is translated into assembly, like what we are seeing here. Are we good so far with that concept? Okay. So this kind of I can kind of mention this a little bit, not to kind of self-advertise the value of this class, but this is one of the values of this class. is to kind of give you an idea of something that you already know, which is short circuit evaluation, but it gives you a reason why that is the case. Okay, so that there's more connection to things that you already understand. All right. So now we talk about simple reductions. In other words, sometimes we do not need to go through the trouble of complicating the control structure to get rid of a logical operator. So if the original condition is it is not the case that x is greater than or equal to y, we can simplify that to simply x is less than y. Okay, so that means I don't need to make the control structure any more complicated because I can simplify the comparison itself so that the negation is gone. Okay, so that's one example. The other example is, if you this is a really obvious one. If the original expression is x is less than y or x is greater than y, well, you might as well just say x does not equal to y. So there's no need to go through the trouble of using the earlier mechanism to convert the OR into something that is more complicated in terms of control structure. So does that make sense? So I would do as much of these conversions, as possible before I go to the earlier approach of complicating the control structure in order to reduce the complexity of the logical operations. So are we still doing okay? All right. So now we talk about comparisons, okay? Because the only thing you can do, the most elemental um, conditional, the most elemental Boolean operations are comparisons, okay? Whether x is less than y, okay? So now we convert everything to less than and equal to, okay? Because what flags do we use to indicate whether a register or value is less than another value? There are two, okay, so which two? So for unsigned, which flag do we use? The Sorry? So this is something that we talked about when we talked about binary comparison, but I also mentioned these, I think, on Tuesday. So if you have not written it down, you might want to write it down because the next exam will most likely involve these things. So the borrow flag, which we know as T something, that is good for unsigned comparison. Okay, so you might want to go back to the binary comparison thing, because that particular module sets T of 8 in this case because we have 8-bit comparison. T8 is true if and only if x is less than y. Now, I have to be more careful because x is a bit pattern, y is a bit pattern. There's no intrinsic value associated with the bit pattern, so I should be saying VU open paren x comma 8 close paren, because that's the unsigned value interpretation of the bit pattern x, and then I have to specify VU open paren y comma 8 close paren to specify the unsigned interpretation of the bit pattern y. So, but nonetheless, the most important part is the borrow flag indicates less than for unsigned comparison. So what flag indicates less than for signed comparison? That should be an easy one. Okay, how many flags do we have left? The Z flag? No, the Z flag only indicates whether those two things are the same or not, so it cannot be that. What about the sign flag? The sign flag it means whether the result is negative or not. But when we talked about binary comparison, we looked at few cases where the sign flag did not tell us the correct result because the difference of the subtraction was out of range. So when the difference of a subtraction is out of range, then the sign flag is going to give us the opposite result. And that's why we need the overflow flag, right? And then we have to combine the sign flag and the overflow flag using exclusive OR. How did I name that flag? The L flag. And L stands for less than. So the L flag is a 1 if and only if the sign interpretation of X is less than the sign interpretation of Y. So this is where we tie this stuff all the way back to binary subtraction. That is one. So this is partially why this class is difficult. It has to do with some earlier concepts that we talked about is relevant at a later point. And by the time we get to the later point, most people would have forgotten. So that means kind of jotting down the notes is going to be it's going to be useful. Okay. Alrighty. So now we go to general compare. Okay, the general compare looks like this. This R is representing one of the two things, which can be a less than or an equal to, because we want to boil everything down to either less than or equal to. So assuming R is less than or equal to, then we can convert it into assembly code like right away. So basically what you need to do is to put the value of X as an expression into a register, put the value of Y as an expression into another register. So assuming you can do that, then the code to implement the comparison is to say compare XY, which means we are subtracting the value of Y from the value of X, but without storing anything back into X. Okay, we're just going through the motion of the subtraction without storing the difference. The difference is just lost, okay, because it's not important to us. And then JRI is not a new instruction. This R, if we're looking for equal to, the R becomes a Z. If we're looking for less than, then the R is either a C or an L. It's a C if it is a signed comparison, and it is an L if it is an, excuse me, I take it back. I just said the reverse. If it is a signed comparison, then we use L, JLI. If it is an unsigned comparison, we use C, which means it is a JCI. Okay, so all of this is important that you capture it in your notes because all of these will become useful basically for the rest of this entire semester. Are we good so far? Say again? For signed comparison, you use L because L is a combination of the sign flag and the overflow. So that's kind of gives you a clue that it is for signed comparison. So if L is for signed comparison, then the other one, which is C, the carry flag, which is also the borrow flag, is for unsigned comparison. So having said all of that, okay, I could have just lied the entire class. So how do you check whether I lied or not? Google, I don't think Google is going to help you much because this is a custom architecture. Hmm? Okay. Or you can do some experiments. Okay. So let me tell you the importance of performing experiments. So performing experiments is important because you get something to do. The design of the experiment itself is already a process of studying because you're thinking about how do I write a very short piece of code in TTP ASM in order to test what I just said. So that means one, you have to at least attempt to understand what I just said. Two, you have to practice assembly language programming. Three, you have to predict the output of the program, right? And then four, you have to go through the motion of executing the program and comparing the outcome of the program with what you expect to be the outcome of the program. All of these steps are important, okay? Now, somebody can say, but once I graduate, once I pass this class with a C or better, I never have to deal with TTP again. That is entirely true. Okay, that's entirely true. Okay, you will never have to program in TTP ASM ever in your life unless you fail the class. But most people who fail this class would go take this class again from a sister college, which I will not name. There of the four colleges, I think one particular college has a super easy version of this class, and I know some people are now thinking, now you tell us. I mean, didn't you guys check rate my professors before you take this class from me? Yes. Too late. I'm I'm the one of the few people with a bimodal distribution when it comes to the rate my professor's rating. Most people have either, oh, excellent professor, everybody just rate really high, or mediocre, kind of in the middle, everybody rate in the middle, or really bad professor, everybody rate out at the bottom. I'm bimodal. It's like there's no one in between. Yes. Huh? Depends on your mood. That sounds like Schrodinger's, mood. Yes. Nope. Well, I for the most part, I really do not care how other people teach this class. So when I have students, complaining to me, it's like, but that's not how other people teach this class at blah blah blah. I go like, do I look like that professor to you? Well, then that answers the question, doesn't it? So anyway, I teach this class the way that I teach it for reasons that I think is relevant. Okay, now whether people agree with it or not, that's entirely up to the individual. Sorry, that's what? It is, well, definitely not my problem. Yes, thank you. So anyway, this R is this R here. Okay, if this is equal to, then R is Z because we are checking for 0. If this is less than, then you have to choose between C versus L, okay, depending on whether it is a signed versus an unsigned comparison. So that's pretty much it. Okay, I have just introduced everything that you need to know to convert control structures into assembly code from C code. So let's check the time. We got about 5 minutes, so that's not really quite enough time to go through an example, but I can do this. I can show you. Oh, this is about nesting and labels. We can go through this maybe next time because I would strongly discourage people to use these as label names because they're awfully confusing. Okay, so what I probably have enough time is to do this. Okay, I think I got enough time to do this. Give me a second to go here. So what I would do is I am going to show you side by side, how to write code in C code and in assembly code. So I think it is a dash uppercase O, um, max.c and versus max.ttp-asm. So I will make this a little bit simple. The original code in C is if A is less than B, then we store C is equals to B because we're finding the maximum. Otherwise, C equals to A. Okay, so this is the original code. So the question now is how do we convert this into assembly code? If you go step by step, it's going to take a little bit of time, and I know you guys are eager to start the lab, so I'm going to do this, all in one shot. So what you need to do, assuming A and B are the registers, they're referencing the registers, you just simply perform a CMP AB, and then if A is not less than B, then we go somewhere else. So this becomes a little bit of a problem because we have a JCI and also a JLI, but there's no JNCI, which means if carry is not set. There's no JNLI either. So that means in this case, you don't really have much of a choice but to say JCI to label L1 and then JMPI to L2 and L1. Let me see. So L1 is going to correspond to the then branch, which means we have a CPR CB. CPR stands for copy register, which copies the second register to the first register. Then we need a JMPI to L3, which is the end of the entire thing. And this is L2. L2 is going to copy register CA instead. And this is where L3 is going to be. So that's kind of, I just went through the whole conversion process in my head, but the equivalent code to the C code looks like that on the right-hand side. Is that okay? All right. So teaching this class, is, I have a super unfair advantage. because I grew up in, I went to high school in the 80s. Yes, so you kind of know how old I am. So in the 80s, there were programmable calculators already. Okay, my friends have they have the FX602P from Casio. Um, it is programmable, but it's not programmable in BASIC, okay, or any high level language. The way conditional statements, are done is very similar to assembly code. So I have been doing assembly language programming since essentially ninth grade. So I have a little bit of an advantage over all of you, just a little bit, yes. And then my before I teach here, my professional job also involves a massive amount of assembly language programming. So yes. Um, well, my dad refused to buy, that kind of calculator because he said, I don't need an expensive calculator. So all my buddies, all my friends, have one. And what they do is they just, they subscribe to some kind of a magazine, and it comes with all the programs already written. So all they did was to copy the program onto the calculator. Typically, they are games, that they can play. So what I did one weekend was, without the manual, was to borrow a calculator from my friend. I got a whole game concept already in my head. I programmed the game over the weekend, and then comes Monday, I return the calculator to my friend. So that's kind of the thing that I like to do. Yes. So now you tell me, Tack, you- All right. So you still need to know the access code of today's lab. There are two components to today's lab. Today's lab is called Absolute Value. So there's one part which is the quiz part, and then the second part is where you need to upload the resulting program. So there are two parts to it. So don't forget the second part. The first part should end up with a program that you can turn in with the second part. Okay? All right. So I'll see all of you at the lab. Yes. Oh, passcode. That's right. Okay, I keep forgetting that. I said I did give you the passcode, and then I forgot to do it. It is ABS, which is also a kind of 3D printing filament.